Imagine you're looking into a mirror. Everything is reversed. Left becomes right, and right becomes left. This simple reflection is how we typically think about symmetry, a one-to-one correspondence, a perfect balance between two sides. It's a concept so fundamental that it has shaped our understanding of nature and the universe, driving scientific breakthroughs in physics, mathematics, and even art for centuries. But symmetry, as it turns out, isn't just a superficial feature of the world we observe. It's deeply embedded in the way we formulate the laws of nature. Over the past century, symmetry has become a guiding principle for physicists, trying to understand everything from the behavior of subatomic particles to the vast structure of the cosmos. One of the most compelling questions that arose from 19th and 20th century physics was, how do the laws of nature stay the same no matter where we are, when we are, or in which direction we're moving? Physicists sought symmetry to make sense of why these laws don't seem to favor one direction of time over the other. If you run the equations of Newtonian mechanics, or even Einstein's theory of relativity backward, they still make sense. Time is symmetric in the equations. Whether you're looking forward or backward, the underlying physics doesn't change. This led to a dualistic understanding of nature. For every force, there's an opposite. For every particle, an antiparticle. For every action, an equal and opposite reaction. These dualities provided a powerful framework for understanding the universe. Symmetry gave us the idea of balance, predictability, and conservation. For example, the conservation of energy and momentum relies on the symmetrical behavior of systems over time. And in quantum mechanics, symmetry helped predict the existence of antimatter, balancing the equations that describe particles. But this framework wasn't without its problems. As our understanding of physics grew more sophisticated, we began encountering puzzles that symmetry, at least in its dualistic form, couldn't fully solve. The most glaring issue was time itself. Yes, equations may work in reverse, but the world doesn't. Time, as we experience it, moves in one direction. We live in a universe where entropy increases, where things decay and evolve. If the laws of physics don't pick a preferred direction for time, why do we? This puzzle led scientists on a quest to find deeper symmetries, ones that could explain not just simple dualistic pairs, but more complex, interconnected systems that could account for the flow of time, the emergence of complexity, and the inherent balance of the universe. We needed a way to move beyond binary oppositions and consider more intricate interactions. And this is where the triad comes in. What if, instead of thinking about balance as a back and forth between two forces, like a pendulum, we began to think about it as the result of three interdependent elements, each influencing and constraining the others? Triadic symmetry offers a richer, more nuanced way to understand how systems achieve balance. In a triadic model, the third element isn't just an afterthought, it's essential. It serves as the constraint, the mediator that stabilizes the other two forces or variables. Without it, the system would collapse or spiral out of control. It's not just balance between two opposites, but balance through a third constraint that ties everything together. For example, think about how we experience force in the physical world. It's not just the product of mass and velocity, as you might think. It's mass times acceleration. But acceleration is itself velocity over time. Time is the hidden third element that constrains the interaction between mass and velocity, allowing force to emerge as a balanced entity. We see this same triadic structure in many physical laws. The ideal gas law, which relates pressure, volume, and temperature, functions because the third element, volume, constrains how pressure and temperature behave. Change the volume of a container, and you immediately affect both the pressure and the temperature. Each of these elements is interdependent and constrained by the third, creating a stable, balanced system. The limitations of dualistic models also show up in more complex systems like quantum mechanics and cosmology. In traditional physics, the introduction of antimatter was essential to maintaining symmetry in equations, leading to an elegant but sometimes problematic idea: for every particle, there's an antiparticle. But antimatter, as predicted by these equations, is incredibly rare in the universe. and its interactions seem more like mathematical necessities than physically pervasive realities. But what if we could reframe this need for opposites? In our triadic model, vacuum potential energy replaces antimatter as the stabilizing force. Instead of needing a mirror image for every particle, the vacuum itself, the so-called empty space, provides the necessary balance. The universe doesn't need a one-to-one match of matter and antimatter. Instead, we see a continuum where manifested particles and latent potential, vacuum energy, dynamically balance each other in a triadic relationship. In this triadic framework, we begin to see the universe not as a set of dual oppositions, but as a system of self-sustaining patterns that emerge from three-way interactions. This applies not only to fundamental forces and particles, but also to more complex emergent systems like life, consciousness, and even social dynamics. Each of these systems can be understood in terms of triadic relationships, where two variables are balanced by a third, ensuring stability and evolution over time. In biology, for example, the interaction between genetic information, environmental stimuli, and metabolic processes forms a triadic system that maintains the homeostasis of living organisms. In cosmology, we could look at the interaction between mass, velocity, and gravitational curvature as a triad governing the dynamics of celestial bodies. Across all these scales, triadic symmetry helps explain how balance is maintained through the dynamic interplay of three forces, each influencing the others in an intricate dance of interdependence. Now let's take this triadic model and see how it applies across different scales, from the smallest building blocks of the universe to the most complex systems we know, like life itself. One of the most exciting aspects of this framework is that it doesn't just apply to subatomic particles or forces in isolation. It operates everywhere, at every level of complexity, creating self-sustaining patterns that allow systems to maintain stability and function. Let's start small. In the world of quantum mechanics, the interactions between particles, fields, and forces are governed by fundamental triads. Take quantum chromodynamics, QCD, for instance. We've already mentioned that quarks interact via three color charges, red, blue, and green. This triadic relationship is what keeps protons and neutrons stable, with the strong force balancing their interactions. Any imbalance in the color charges would destabilize the particle, but the system achieves stability through this triadic interaction, ensuring that these particles stay bound together within the atomic nucleus. But what's interesting here is not just the balance itself, but how this interaction is self-sustaining. If one color charge shifts or changes, the other two immediately adjust. This triad doesn't require external intervention to keep it balanced. It dynamically adjusts itself to maintain stability. This is the essence of self-sustaining patterns. Systems that adjust internally to external changes in a way that maintains balance. Now, let's scale this up. Think about thermodynamic systems where energy is exchanged in the form of heat and work. Here we have another triadic relationship: heat, work, and internal energy. The first law of thermodynamics tells us that the change in a system's internal energy is equal to the heat added to the system minus the work done by the system. Once again, the system sustains itself by balancing the flow of energy between these three components. The system doesn't need an external force to create equilibrium. This triadic relationship inherently allows the system to respond to changes in heat and work while maintaining its internal energy. Now, imagine scaling this further to something as complex as an ecosystem. In ecosystems, energy flows, species populations, and environmental conditions form a triadic relationship that sustains life. Energy from the sun flows into the ecosystem, feeding primary producers, which in turn support herbivores and predators. At the same time, environmental conditions, like temperature, water availability, and nutrient levels, constrain and shape these interactions. If one element shifts, say a sudden change in temperature, the entire system responds, adjusting energy flows and population sizes to re-establish equilibrium. Once again, the system sustains itself dynamically, maintaining a balance between its components. At every level, from the quantum to the thermodynamic to the ecological, we see this triadic balance at work, enabling systems to sustain themselves over time. The magic of these patterns is that they emerge naturally from the interplay of the three components. No single element dominates. Instead, each one contributes to the stability of the whole. And this isn't confined to physical systems. Social, economic, and biological systems all exhibit similar triadic patterns that maintain balance while allowing for dynamic change. But how do these self-sustaining patterns remain stable over time? What keeps them from falling apart under pressure, change, or disruption? This brings us to the concept of topological stability and homeostasis, ideas that help explain how systems maintain their structure even as they evolve. Let's first talk about topological stability. Topology, in simple terms, is the study of how shapes and structures maintain their integrity even when they are deformed. Imagine a rubber band. You can stretch it, twist it, or bend it, but it retains its essential shape unless you cut it or tear it apart. Similarly, systems that exhibit topological stability can withstand changes without losing their fundamental properties. In physics, this concept is analogous to the behavior of solitons, self-reinforcing waves that maintain their shape even as they travel through a medium. Solitons are fascinating because they resist dissipation. Unlike regular waves, they don't break down or lose energy as they move. This kind of persistence through change is precisely what we see in triadic systems. The balance between the three components creates a stable structure that can adapt to changes but doesn't lose its overall form. Think back to our example of force in Newton's second law. If we alter mass or acceleration, the force adjusts accordingly to maintain the relationship. This isn't a static system, but a dynamic one, where changes don't lead to breakdown but instead drive an adaptive response that sustains the system's balance. The system remains stable because it's topologically robust. It can bend without breaking. But beyond physics, this concept of topological stability applies to more complex systems like biology. One of the best examples of this is homeostasis in living organisms. In biological systems, homeostasis is the ability of an organism to maintain internal balance despite changes in the external environment. This could be something as basic as maintaining body temperature in the face of fluctuating weather, or as complex as regulating blood sugar levels through the interplay of insulin, glucose, and metabolic processes. What's remarkable about homeostasis is that it too operates through triadic relationships. Take the regulation of blood sugar. The pancreas, glucose, and insulin form a triadic system that adjusts dynamically to keep sugar levels stable. If glucose levels rise, the pancreas releases insulin, which helps cells absorb glucose, bringing the system back into balance. This dynamic process ensures that even when the system is under stress, like after eating a large meal, it can restore balance, sustaining life. The stability we see in these systems doesn't come from rigid structures or external controls, but from the internal feedback loops that constantly adjust the relationships between the system's components. Each element of the triad exerts influence on the others, and when one changes, the system adjusts to maintain equilibrium. This self-adjusting feedback is the hallmark of homeostasis, and it's why triadic systems are so stable over time. Now let's scale up again. In cosmology, we encounter the same kind of self-sustaining stability when we look at the gravitational forces that govern galaxies. The interaction between a galaxy's mass, velocity, and gravitational curvature forms a triadic relationship that determines its structure and behavior. The galaxy's rotation is balanced by its mass and the curvature of space-time, with gravity serving as the constraining force that holds everything together. Even in the dynamic, evolving universe, these triadic relationships ensure that galaxies don't collapse into chaos. They maintain their form over billions of years. What's common to all these examples, from quantum mechanics to ecosystems to galaxies, is the idea that stability isn't passive, it's active. It's the result of constant dynamic feedback where each element of the system adjusts to changes in the others. And at the heart of this stability is the triadic structure that governs the interaction. These systems can withstand disruption because they don't rely on static balance. They rely on adaptive topological stability that allows them to change and evolve without losing their fundamental structure. So whether we're talking about subatomic particles or living organisms, triadic symmetry provides the foundation for both stability and adaptability. It's the mechanism that allows systems to remain stable while responding to changes, and it's the reason why these systems persist across time and scales. Now, let's shift our focus to one of the most intriguing concepts in modern physics, antimatter. When it was first predicted by Paul Dirac in the early 20th century, antimatter seemed like a brilliant, almost poetic solution to a symmetry problem in quantum mechanics. The equations that describe particles, like electrons, didn't quite balance without the existence of a mirror counterpart, an antiparticle, identical in mass but opposite in charge. This prediction was later confirmed with the discovery of the positron, the electron's antiparticle. And from there, the idea took off. Every particle, it seemed, had an antimatter twin. But as elegant as this symmetry appeared mathematically, it soon introduced new puzzles. If every particle has an antiparticle, why don't we see as much antimatter in the universe as we see matter? Why does our universe appear to be made almost entirely of matter, with antimatter so rarely observed? To make things more complicated, when matter and antimatter meet, they annihilate each other, converting into pure energy. This raises the question, how did the universe survive long enough to form stars, planets, and life if equal amounts of matter and antimatter were created in the Big Bang? Why didn't everything annihilate immediately? These were fundamental issues for a dualistic model of symmetry. Antimatter had to exist to balance the equations, but its scarcity raised deep questions about the nature of reality. What if, instead of requiring a one-to-one counterpart for every particle, we took a different approach, one that doesn't rely on strict binary oppositions? This is where the triadic model offers a new way of thinking about the role of antimatter in the universe. Instead of seeing antimatter as the mirror opposite of matter, what if we viewed it as part of a broader triadic system, where balance is achieved not through direct opposition, but through the dynamic interaction of three elements? In our triadic model, antimatter is reinterpreted as part of the vacuum potential energy, the underlying field of possibilities that exists in every system. Instead of antimatter being a separate mirror universe that exists alongside matter, we see it as a kind of latent potential within the fabric of space itself. This reimagining solves some of the paradoxes posed by the dualistic view of antimatter. Here's how it works. In our triadic framework, matter is one part of the system, the vacuum is another, and the third element is the dynamic process of interaction between them. The vacuum isn't a void or absence, it's a reservoir of potential energy. This potential doesn't need to manifest as antimatter to balance matter. Instead, it acts as a stabilizing field, ready to influence interactions as needed, but not requiring the existence of an equal amount of antimatter to cancel out matter. Imagine the vacuum as a kind of latent potential that's always there, influencing the behavior of particles without needing to take form itself. This continuum of energy that permeates the vacuum is what balances the equation, not a physical mirror image counterpart for every particle. By reinterpreting antimatter this way, we remove the need for a destructive duality where particles and antiparticles are constantly poised to annihilate each other. In this triadic system, negation is not about two forces canceling each other out, as in the case of matter and antimatter annihilation. Instead, negation is better understood as vacuum potential energy, the unseen but always present possibility within the system. For example, when you look at quantum field theory, particles are often described as excitations in a field. In this view, particles, matter, are just one state of the field, while the vacuum represents another latent state. The triadic model allows us to think of vacuum energy as part of the same system rather than something that opposes particles directly. It's a balancing force, but not a destructive one. The vacuum isn't nothing. It's a source of potential available to stabilize and interact with matter without needing to manifest as antimatter. This reinterpretation of antimatter resolves many issues that arise from the traditional dualistic approach. We no longer need to ask why we don't see equal amounts of matter and antimatter in the universe. the vacuum potential takes over the role of stabilizing the system, allowing the universe to maintain balance without annihilation. This brings us to a deeper philosophical shift that underpins the triadic model, the energy continuum. In traditional physics, we often think of forces and particles in terms of binary opposites. Matter and antimatter, positive and negative charge, north and south poles, they are all part of a dualistic framework. But this way of thinking creates hard boundaries between entities that are, in reality, part of a continuous spectrum. In a triadic model, we see energy as existing on a continuum. Instead of rigid opposites, we understand that matter and vacuum potential are two aspects of the same system. The balance between them is mediated by a third dynamic process that connects and stabilizes them. This continuum-based view provides a more fluid and integrated way to understand how the universe operates. Let's return to the idea of force as an example. In Newton's second law, force equals mass times acceleration. But acceleration itself is a change in velocity over time. There is no hard boundary between these components. Time is the constraint that links mass and velocity, allowing force to emerge as a balanced result of their interaction. Similarly, in our triadic model, energy flows between matter and vacuum potential, constrained by the dynamic process that links them. There is no hard divide, no strict opposition, just a continuous flow of energy that keeps the system stable and balanced. This also changes how we think about entropy and order. In a dualistic framework, we often view entropy as the opposite of order, a force that drives systems toward chaos and disorder. But in a triadic system, entropy becomes part of the continuum, a balancing force that ensures systems can adapt, evolve, and maintain stability over time. It's not the enemy of order, but a necessary part of the dynamic balance that sustains life, motion, and change in the universe. A triadic approach also removes the idea of destructive annihilation from the equation. In the dualistic model, matter and antimatter exist in constant tension, where their interaction results in mutual destruction. But in a triadic model, the relationship between matter and vacuum potential is not antagonistic. Instead, it's complementary. The vacuum provides the latent energy that can stabilize and sustain matter without needing to annihilate it. In this way, the universe becomes a place of dynamic balance, where energy is not constantly being destroyed or opposed, but is instead flowing smoothly across a continuum. Matter and vacuum potential are part of the same whole, interacting in a way that maintains the system's homeostasis without the need for destructive processes. This is a more holistic and, in many ways, more optimistic view of the universe. A universe where balance is maintained not through opposition, but through integration.